All right, so we are jumping into chapter 2 of our book. And before we get into the big bulk of chapter 2, we have section 2.1, which is like a one lesson section. Only lessons 2.1. It's a little bit longer than usual because there's more that goes into it. But in this section, we're going to talk about something called location in a distribution. So I want you to picture the following kind of hypothetical scenario here. Say you're in a big college class. You're going to college, you're in a big math class, and you just took a huge test. Next class, professor passed back the test to you, and you see on your test that you got a 37%. So when you see that 37%, your heart is probably naturally just going to sink, and you're just going to feel awful about that. Like, oh my gosh, this is just the worst. Oh, the world's going to end. This is just so terrible. And you would be pretty upset about that. But then the professor finishes passing back the papers and gets back in front of the class, and they say that the highest grade in the class was a 37%. So now, all of a sudden, that score that you were just so upset about looks really, really good. You got the highest grade in the class. And there's probably going to be a curve. You're going to end up doing really well, and you feel so much difference about that score that just a second ago you were really upset about. The idea of a raw score, knowing your actual value, is important. But what's almost as important as knowing your actual value is how you compare to all the other data points that are out there. Another quick example is the SAT. Most of you probably haven't taken the SAT. We're in the Midwest. That's a lot. The ACT is a lot more common and popular here. So if I told you you're going to get a 1300 on your ACT or your SAT, you're probably looking at that like, okay, is that good? Is it bad? Is it in the middle? So knowing how you would compare to other people is an important part of analyzing data. And the name we give to that is describing location. Where am I with respect to other points? So that's what we're going to get into in this section. There are going to be two main methods that we use to describe location. The first of which is called a percentile. And percentile is a topic that I see even adults misuse or misunderstand pretty frequently. So it's a topic that isn't that bad, but people do get tripped up on it. So hopefully you're already semi-familiar with the concept. But what I want you guys to write down here to kick things off, when you talk about a percentile, you want to look at what percent of data points are less than or equal to me. What percent of data points are less than or equal to me? In my example that I just gave about the university class, you got a 37%. That 37 has nothing to do with your percentile. Percentile is all about what percent of people are you better than, or did you beat, or at least tie. So in the example, if you were the highest grade in the class, you would be at the 100th percentile because you are greater than or equal to everybody in the class, 100% of the class. Okay. If you got like a 32 in that same class and a 32 puts you at the 85th percentile, that would mean that 85% of kids got a 32 or lower. Quick sidebar on this, the definition of percentile is a little fuzzy depending on what book you read or what website you look at. Sometimes instead of just less than or equal to, you will see just less than. So it can change depending on what book or source you've read. Even when I taught this, before I'm making this video right now, I've always used less than because that's what our textbook has said to do, and that's what a lot of people do. But the AP board has made the change that it is now less than or equal to when you do percentiles. But be aware, if you read my old answer keys and stuff, I might have used just less than because that's how it used to be taught. So anyway, with that kind of out of the way, I have a couple comments here on percentiles, and then we'll look at an example. So when you're talking about percentiles, I'm especially guilty of this. I might have done it in this video already. I don't remember. But the thing that pops up a lot is you might actually accidentally say you're in the 50th percentile or in the 70th percentile. You're not supposed to say in with respect to percentiles. You're supposed to say at the 30th or 50th or 70th percentile. A percentile is a location mark for telling you where you're above a certain percent of people. You're not in that percentile. So that's just a nitpicky vocab thing. Also, when we talk about percentiles, we generally round them to the nearest whole number. We don't bring decimal like 42.7th percentile into it. So let's do an example. What we have here is a list of the 30 Major League Baseball teams and how many games they won in the year 2009. So we have a key right here that tells us, 5-9 is 59 wins. We always include keys when we make our graphs. And we're asked to calculate and interpret the percentiles for the Rockies, the Yankees, and the Cleveland Indians. So let's start and do one of these together, and maybe you can pause me and try the rest of them out. So if I'm the Colorado Rockies with 92 wins, that is me right here. I need to look at what percent of teams got my score or worse, and that'll be the percentile. Okay, so I could count up. I beat this team, that 59. I totally beat. That's 1, 2, 3, 4, 5, etc. 6, 7, 8. Or I could also just count the teams I didn't beat. 1, 2, 3, 4, 5. If I didn't beat 5 teams, that means I did beat 25 teams. So it's myself and the 24 teams below me. So for the Rockies, I'm greater than or equal to 25 out of 30 teams. And then I just divide that to turn that into a percentile. So I don't have my calculator super handy here. I'm going to pull it up real fast on my phone. But you guys can go ahead and try out those other two yourself, and then we'll talk about interpretations here. So find the value that you care about and figure out what percent of people you're greater than or equal to. I got for my Rockies example, it was 83.3. So that puts me at the 83rd percentile. And again, please calculate the other two yourself, and I will talk through them, but pause me if you need a little bit of time here. Next up is the Yankees. And for the Yankees, they have 103 wins. They are the best team in baseball. They are greater than or equal to all 30 of the teams. So that puts them at the 100th percentile. If you're at the 100th percentile, you are greater than or equal to everybody. For the ACT, getting a 36 on the test would put you at the 100th percentile. And then lastly, we have the Cleveland Indians, and Cleveland's was at 65 wins. People will sometimes look at this and be like, well, which 65 is it for them? It doesn't matter which one they are, because when you count teams that they're greater than or equal to, they're greater than this, equal to this. So there's 5 teams out of 30 that they are greater than or equal to, and 5 out of 30 is 16.6 repeating. So that is the 17th percentile. So a percentile has nothing to do with very little to do with your actual score. It has everything to do with what percent of scores you are greater than or equal to. So when I look at this problem here, I'll interpret one of these just so you guys can see how it's done. The Rockies won as many or more games than 83% of teams in the MLB. You certainly can word that in other ways. Like if you wanted to say 83% of teams scored less than or equal to, or got less than or equal to the Rockies' number of wins, that's totally fine too. You just basically are talking about the percentage of the total that fall there or lower. And that's how you interpret a percentile. So percentiles are good. A quick comment on them. When you have really small data sets, percentiles get kind of weird. Like they get kind of strange looking. Like for example, let's say I only had 4 data points right here. So if I only have 4 data points, I can be at this point right here, which is the 25th percentile. I'm better than 1 out of 4 teams, the 50th percentile, the 75th percentile, or the 100th percentile, and nothing else in between. And I can make lots of other weird examples where it just, like when your data set is too small, a percentile isn't that good. Where percentiles really shine is in really big data sets. Like with ACT score, you're comparing yourself against like millions of kids across the country. So you should get a pretty good sense of where you stand when the data set is big enough. All right. So we may be asked to interpret percentiles not only just like through a little data set, but also through looking at graphs. The official name of this graph is called a cumulative relative frequency graph, written right here. But the phrase cumulative relative frequency means percentile. A relative frequency is a percent. A cumulative relative frequency is a percentile. Okay? So that phrase right there is one you need to know. Cumulative relative frequency means percentile. And what we're going to do right here, these kind of graphs always only increase. So when they start down here at 0, they will never dip back downwards. They only can increase. It's just how steep they are as they do so. And on the left right here, going vertically, cumulative relative frequency is percentile. So this is the 0th percentile, the 20th percentile, the 40th, the 60th, etc. So let's look at this problem right here. It says California has a median household income of $57,000. And we've got all 50 states plus DC on this graph right here. 57.4 would be, that's 57.5 right there. So 57.4 is going to be just shy of that tick mark. And this is going to be bad because it's hard to draw straight with this. Let's see how I do. It's not too bad. So I would figure out where 57.4 is for California on this graph. And then once I have that, I'm going to follow completely horizontally. It's a little less nice. Till about right there. And that'll tell me what percentile California is at. So it's going to be based on my wobbly line right here, a little under the 80th percentile. So I'm going to call this maybe like the 78th percentile. You certainly could be a little higher or a little lower, depending on how you drew that. So I'm going to interpret this in a slightly different way than last time, just so you can see different styles. 78% of states have median income less than or equal to that of California. In other words, if I'm California, my median income is better than or equal, I'm greater than or equal to 78% of the other states. So if we were going to rank all the states, California would be kind of close to the top. They're better than 78% or equal to 78% of the others. Then on this next question here, I say, what is the 25th percentile of this distribution? Well, if I give you a percentile, you're just using the picture backwards. That's 30% right here. So 25th percentile would be right here. And I do the same sort of thing. I just follow it to the graph, trying to be as straight with my lines as I can. That wasn't super great there, but I'm going to call it somewhere in the neighborhood of 4,600. 46,000. So it's about 46,000, although I could be off depending on how wobbly my lines are right there. What is another name for the 25th percentile? This is reminding you, we talked about it a little bit last chapter, but we had that idea of a 5-number summary in Q1, Q2, Q3. Those were the 25, 50, and 75th percent marks. So the 25th percentile is exactly Q1. Okay, I could ask you to find something like the median from this graph. I would find my 50th percentile. I could do Q3. I could do IQR. All of those things you could be able to find when you're looking at one of these pictures. So let me tab to my next page, but I'm going to come right back here because the two next questions both use my graph, and I want to have that handy. So I ask, where is the graph the steepest, and what does that tell you about your distribution? And I ask to make a relative frequency histogram. So I'll show you how both of those things work using this slide right here. So first of all, where is this graph the steepest? This graph to me appears to be the steepest. It's going to be one of these parts right here. I think it's this one. That's the steepest portion right here. So if we look at the bottom dots right here in that's going to be maybe like, I'm going to call it the 22nd percentile. And if we look up here, that is like the 47th to 48th or somewhere in that range. So between 45,000 and 50,000, we jump from 22nd percentile all the way to 47. Okay, and those are my estimates. What does that mean? It means that lots of states must live in that little section of the graph right there. Because you're leapfrogging with just 5,000 extra dollars, you leapfrog from only beating 22% or meeting 22% to 47, which is a pretty significant jump. So on that next page where it asks which section is cheapest or steepest, it's from 45 to 50K. And what does that tell you? The most states fall in this range. When you get to see much less steep parts, like this guy over here, that means there weren't very many states in that range because you increase about the same amount right there in money, but you don't beat that many more states. Okay, so steep means lots of people there. Shallow means not very many there. And the next question asks us to turn this into a histogram, which I'm not going to do the whole thing on, but I do want to show you how that would work. When you make a histogram with this, you're going to have for your axes, I'll put it over here, your bottom axis is going to mirror what you do on the percentile graph. So I would still have 35, 40, 45, 50, exactly like they're doing down here. This part doesn't change. What I would want to do is look at the percentile for each of the dots at these dividers. I'm at the 0 mark. This is definitely less than 10. I'm going to call this like the fourth percentile. 22, I think I called this 47, and then 71, I don't know. You just mark your percentiles for each one. Now, if you look at that first graph, I'm going from the 0 to the 4th percentile. That means 4% of my states must live in this range right here. So on this axis, the y, instead of your standard percentiles, this is just going to be straight up percentages instead of percentiles. And 4% of my teams or states live in that range. Then my next one goes from 4 to 22. 4 to 22 is 18 if you subtract it right there. So my next bar would go up to 0.18. And then after that, 22 to 47 is a 25. So my next bar goes up to 25%, etc. So you just basically do a little subtraction if you mark the picture here, and you can transfer this info and turn it into regular percentages instead. So that is our discussion on percentiles. For this second part of the lesson, we're going to kind of switch gears right here. So we're going to go from talking about percentiles to a totally different way of measuring location in a distribution. This one is we actually use even more than percentiles in this class. So let's get to it. So we have a little girl and we have her older brother, and it gives their heights in centimeters. So we have 100 centimeters for her, and then her 12-year-old brother is 158. And it's not very surprising at all that a 12-year-old boy is taller than a 3-year-old girl. That's not surprising in the least. But just because he's taller than her doesn't mean he's taller than her, relatively speaking. What do I mean by that, relatively speaking? Well, compared to other 12-year-olds, we want to know how tall this kid is going to be. Is he the tallest one in his class where, wow, you're really tall for a 12-year-old? Or is he relatively short? He's the shortest one in his class where he's not tall by 12-year-old boy standards. So it's another situation where you want to compare apples to apples here and not have this 12-year-old boy being compared straight up to a 3-year-old girl. Maybe the 3-year-old is like the tallest 3-year-old ever, and it's just she's taller, relatively speaking, in her age group. So let's think about how we would do this. If we want to know how tall they are with respect to their peers, we would need to know what the average height is for that age range, and they give it to us in the problem. So the average height for 3-year-old females is 94.5 centimeters, which is good. I couldn't tell you if this is tall or not tall, but now we have an average to compare to. And the standard deviation is 4 centimeters. So this is the info for the girl. And then for the 12-year-old, the average height is here. Standard deviation is here. So let's talk about what we can do with these numbers. Let's take the 3-year-old first. She is 100 tall, but 94.5 is the average. So if you would actually subtract that, She is, what would that be? That's 5.5 inches or centimeters, sorry, 5.5 centimeters above average. But when you look at just the averages there, there's another thing you have to consider to go along with this. If you're 3 years old, you don't see too many like 6 foot 3 year olds. Doesn't happen because 3 year olds in general are closer to each other in their heights. You're going to have naturally less spread in that data set than you are in 12 year olds or in adults where there's a lot more range to the possibilities. 3 year olds aren't that different in heights, from my understanding. So, not only do we care about the average, but we want to look at with respect to the standard deviation, how far they are from the norm. So, what I'm going to do is take this difference of 5.5 and I'm going to divide it by the standard deviation. And if you divide that, so we do 5.5 divided by the standard deviation of 4, this gets us 1.375. What does that number mean? Well, I'm 5.5 centimeters above average, and the average or typical distance from the average is 4. So 1.35, if I was a 1 for my, I'll tell you what this is called in a minute, but if I was a 1 for this value right here, that would mean that I'm pretty typical. Because the typical distance is about 4. I'm 4 away, so I'm very typical in how far I am from the average. I'm a little more than that, though. I'm 5.5 away, so I'm a little bit taller than average, relatively speaking. This measures the number of standard deviations you are from the mean, and it's actually a concept called a z-score, which we'll formalize on the next slide. Let's look at the boy, though. So for the boy in this problem, he is 158, and then 149 is the average. So he's 9 above the average, but the standard deviation is 9, and 9 over 9 is exactly 1. So he's taller than average, definitely. He's 158, the average is 149, but he's not as special in terms of heights because the typical distance from the mean is 9, and that's exactly what he is. So when you look at this problem, even though obviously 12-year-old is taller, the 3-year-old is actually taller with respect to her peers. She's 1.375 standard deviations away, where he is only 1 standard deviation away. So as I referenced, this is called a z-score. And a z-score is also called a standardized score. So when we talk about standardizing something in general, we're talking about finding a z-score. The variable we use for a z-score is very appropriately a z. And the formula for a z-score is written x minus mu divided by standard deviation. X stands for your value. So just a second ago, I took the girl's height of 100 minus the average of 94.5. Her value goes here, the average or mean goes here, and the standard deviation goes on the bottom. So when you get a z-score, what it does is it tells you how many standard deviations a data point is above or below the mean. So the z-score uses mean and standard deviation, who are like our two best friends in statistics. We use them all the time. And it tells you how many standard deviations away you are. So a bigger z-score means you're farther from the average, accounting for the variability of your data sets. Okay? So when you take the z-score for the girl and for the boy, you put them on the same playing field, hence the name standardized. So now you can compare them and be like, oh, the girl is actually taller with respect to her peers. When you find a z-score, you're going to talk about how many standard deviations it is above or below the mean. And I do say below the mean here too. Both of our kids in this problem had positive z-scores because they were taller than average. But picture if I had a shorter kid who was like, I don't know, I think, so the average was a 94.5. Let's say my kid was only 90 tall. Well, when you do that, you are most definitely going to get a negative z-score, negative 4.5 divided by 4. So you can have a negative z-score. That just means you're smaller than the mean. Standard deviation has to be positive, but a z-score can totally be negative in a problem. Okay, so we have an example here to practice this, and we are looking at the home run race in baseball. I don't know how familiar you guys are, how closely you follow it, at the home run record for baseball. And we have here on this list at the bottom the top 4 home run hitters of all time. But these 4 home run hitters came from very different time periods. Babe Ruth was 1927, Roger Maris in 61, and then McGuire 98, Barry Bonds. I can't see it right there. I think that was 03 though. In the early 2000s. Oh, wait, did it say somewhere? 2001. So obviously, Barry Bonds has the most home runs. But there's a lot of factors that go into baseball, and a bunch of the stuff is written on this slide right here. But you can look at things like the ballparks, how big they were, the type of ball they used at the time, because they changed the composition of it. Stuff about steroids, stuff about like different the talent level of the pitchers. There's a lot of factors where you can look at these ball players playing in like totally different eras, and it's really kind of hard to compare them well. So what we're going to do to make them kind of all on the same playing field right here is we're going to compare them on the same scale. So we are going to take into account the average number of home runs hit at that time, and then we are also going to account for the average standard deviation. And we're going to see who is actually the best right here. So I'll show you that with the first problem, and I will compare. So I'll do the first one here and show you how that's set up, and I'll have you guys do the other ones. And I'll pause myself and write down the answers. So if I wanted the z-score for Babe Ruth, I would take his value, which is 60. I would subtract the mean from 1927 of 7.2, and I would divide by the standard deviation of 9.7. And if you calculate this, it'll get you a z-score. Make sure, obviously, you hit enter before you divide. So find his z-score and find the other 3's as well, and then we will make a comparison. All right, so I've got all 4 answers written down right here, and I went ahead and showed work for at least the first 2, so you guys can see what's going on. Let's talk again about what these numbers even mean. Having a z-score anywhere in the 3's is a really big deal. What that means is you have your typical distance from the mean. You are 3 times that distance, and they're all positives. So they're all way above the mean right here. That shouldn't be surprising if you look at the number of home runs that they all hit. These guys are all legends who have hit tons of home runs. But when you account for the mean and the standard deviation of the other players at the time, one of these numbers absolutely jumps out. This is Babe Ruth right here with the 5.44. And when you look at a z-score of 5.44, it is unreal how much better he was than everybody else around him at the time. His 60 home runs, when the average was only 7 home runs a year for a player, is way more impressive and way crazier than looking at some of these others, which are also like just amazing numbers. So you could get into a whole debate here, which is not the purpose of this. Like at the time in the 20s, they're probably the other baseball players weren't as good. The pitching wasn't as good. Like it's not a baseball lesson right here. So I don't need to get into the specifics of that. But when you account for the home runs that everybody else was hitting at the time, his number, Babe Ruth's number, is way more impressive, relatively speaking. That phrase, relatively speaking, gets used a lot when you talk about z-scores. Compared to his peers, he was more impressive and more like, they're all impressive, but the most like outside the norm. Okay?